All right, Matthew, this one's for you. So I'm going to explain time dilation and relativity. This basically is how time passes differently depending on how fast you're moving compared to someone else. And so I broke this into 3 parts. So we've got inertial reference frame, consistency of the speed of light, and then time dilation, derivation, and examples. So the first part to understanding relativity is the inertial reference frame. And here we have 3 reference frames. So a person standing on the side of the road, one car moving at 90 meters per second, and the other car moving at 100 meters per second. Each of them experiences motion differently depending on their frame of reference. So, I'll give an example. So the man that's standing on the side of the road, he can view the car that's going 90 meters per second as 90 meters per second, and the guy going 100 meters per second as 100 meters per second. However, the guy driving the yellow car going 90 meters per second views the blue car as only going 10 meters per second because his point of reference is already 90 and the blue car is only doing 10 more than him. So you have to understand that there are different points of reference when trying to understand relativity. So one of the strangest things about physics is that the speed of light is the same for everyone, no matter how fast they're moving. So for example, a person on Earth and a person traveling in a spaceship, even at 99% of speed of light, both measure light as moving at the same speed. And if that's true, then their experience of time must change to make the math work. And that's what we call time dilation. The faster you move towards the speed of light, the slower time will pass for you. And that's the basis of time dilation. So here's a example that I worked out. So imagine that there's one person inside of a spaceship and another person on the Earth, right? So a laser shoots up and bounces off of a mirror and then goes back to a detector. And that's inside of the spaceship. And let's just, for giggles, let's pretend that the person on the Earth can see inside of the spaceship, all right? So what we have inside of the spaceship is, that time is equal to the distance over the speed, right? And so we can take 2 times that distance, right? Because it has to go up and it has to come back down after it reflects. So that's where we get the 2 from. And then we're going to divide that by the speed, which is the speed of light, right? And we're going to say that the total change in time, right, is that 2d over c. And this is the change in delta t naught. And that's basically just representing the time inside of the spaceship that the person views, right? Now, when we get over to the Earth, it's a lot different because you have to understand that this rocket ship is actually traveling around the Earth at a certain speed. So let's say the rocket ship starts here and he travels over here. Well, the person on the Earth is viewing that vertical motion, right? That one that's right there. But since he's moving at such an incredible speed that way, he actually sees it as kind of like a triangle wave, like a beam. So it might start here, go there, and go there. And these formulas are just based on Pythagorean theorem. I'm not going to go too into detail and bore you on that. But anyways, the earthbound observer sees time in this fashion rather than this. So we can obviously see that it's more complex and it's going to be a larger amount of time on the Earth just from how much is up here rather than here. So dilation is to expand So for the person on the Earth, the time interval change in t has been expanded relative to the change t naught. So in other words, if you had a clock on the spaceship, it would run slower because this is the only way for both observers to get the same speed of light. And I've got an example here that will prove that. Now, when you see these movies, where they go off into space for, I don't know, a year and then come back to Earth and it's like 40, 50, 60, 100 years later, that's not really accurate. But it does work that way. So let's say a person in a spaceship is moving at 80% speed of light. And let's say they are doing that for a year. Let's say they're orbiting the Earth for a year. And that 1 year is measured on the spaceship. So how long will it be for someone on the Earth? Well, let's take that formula we got there and let's plug our stuff in. So we have 1 year. And v squared, our velocity squared, is 80% speed of light. Right, something like that. And finally, we get it all the way down to 1 year divided by 0.6. And that final change in t viewed from the person on the Earth, 1.67 years. So in other words, when you're moving at 80% speed of light for 1 year around the Earth, someone on the Earth is going to view that as 1.67 years. So in fact, it actually is a longer amount of time for the person on the Earth.